All right, it looks like we're okay. The countdown works. We're okay. All right. Okay, so we left off on Friday, and we said that let's say we're talking about this baseball player, okay, who had 4 hits out of 10 at bats, okay, and we don't know what his true kind of batting average is. And in Bayesian statistics, all we can do is we can say this player's batting average follows this probability distribution. The probability distribution says the batting average of around 0.27 is very likely, where a batting average around 0.25 is also likely, but a batting average of 0.4 is very unlikely, and a batting average of 0.15 or something is also very unlikely. But it doesn't say exactly what that batting average is, and it could be any value really between 0 and 1, but much more likely it's something between 0.2 something, 0.2 and 0.35-ish, probably closer to 0.27 or something around there. Okay. We contrasted that to frequentist statistics, where if we wanted to ask this question, what's the probability that the player will get 2 hits in the next 3 at-bats, all we have to do is we just take in a single number estimate, in this case 0.4, based on the data we've seen, and we just plug it in and we get a number back. Okay. And now we're in this situation where we still want to answer this question, what's the probability of getting 2 hits in the next 3 at-bats, except this time we don't know what P is. We just know P can be any value between 0 and 1. And it's much more likely that, that it's something around 0.27, maybe a little higher, maybe a little bit lower. So how can we use that information, that distribution of P, to answer this question? All right. Just stretching? Okay. There was a panicked look of, oh, I'm accidentally raising my hand here. Okay. All right. So the question again is, so I'm going to just write some player has 4 hits in 10 at-bats. Okay. Okay, which means we have 6 outs. 4 hits, 6 outs. The prior distribution for the player's batting average is beta 81 to 19, and then after observing 4 hits and 6 outs, our posterior distribution is beta 85 to 25, okay? And we got this by multiplying the likelihood of our data times the prior PDF. Okay. Okay, so far so good? Any questions like how did we get to 85 to 25? We're okay there? All right, and so and now our question is, if the player has 3 at-bats, what is the probability the player will get 2 hits? Okay. And so this question, if the player has 3 at-bats, what's the probability the player will get 2 hits? This is going to be a binomial question where n is equal to 3, x is equal to 2, and p is unknown. Okay. So so our answer is going to be 3 choose 2, p to the 2 times 1 minus p to the 1. Okay. So, I mean, we can simplify this. We don't have to. But this becomes 3 p squared minus p cubed. Is that right? Did I do my multiplication correctly? Okay. So that's what we have, right? So this is what our answer is, except we don't know what p is, right? If we knew what p is, this is easy. We can just plug in p and we get an answer. But we don't. All right? All we know is that p comes from the distribution beta 85 to 25. Okay. Okay. So what do we do? I have to think back probably to like 100b. Okay. How do we define the mean? How do we calculate the mean? So put this thought on hold, and so just kind of go back to 100b. All right. So if we say if p comes from beta 85 to 25, which means the PDF is that f of p is going to be 1 over p 85 to 25, and we have p to the 85 minus 1 and 1 minus p to the 225 minus 1. So this is our PDF. How do we find the expected value?
Integral from 0 to 1.
Yeah, what is the expected value of p? Maybe I'll use square brackets, I guess. Okay, so the expected value of p, which we might say mu sub p or whatever you want to call it, this is going to be the integral from 0 to 1 of what?
P times f of p.
P times f of p dp, right? Okay. If we wanted, what is the variance? What do we do?
Integral of that p squared f of p minus.
Yeah, so now we have p minus mu sub p squared f of p dp, and it can actually equal b, this can be simplified to e of p, wait, I always get
p squared.
p squared
Yeah.
minus e of p quantity squared, right?
Yeah.
Okay, and if we wanted this part could will be 0 to 1. How do we get this? Of p squared f of p dp, right? You don't have to write all of these notes down, right? This should be review, maybe. Should be. Okay. All right. So now the question is, what is, okay, what if, so the general form though, okay, is what is going to be, if we have some function h of p, how do we calculate this?
Integral negative infinity to infinity.
Yeah, so,
P.
yeah, so this is, and assuming p comes from beta, right? All right, so this will be integral from 0 to 1 of h of p times basically the distribution of p, right? Okay, or you know, more generally, the integral from negative infinity to infinity of basically, I'm going to just switch to h of x and f of x dx, right? So if this will be the expected value of h of x, like this. Is that all right? Do we feel okay with all of this? All right. So, because technically, I can rewrite the variance as the expected value of p minus mu squared, right? That's all we're doing. Okay, so let's bring this back, and I'm going to show. So this is from the textbook, introducing. It's from this book, okay? Introducing Monte Carlo methods with R. I'm going to do things a little bit out of order. I think it's okay, all right? We're going to start with this, classical Monte Carlo integration. And this is what we want, okay? This is the thing that we are after. Okay, and let me just write a few things, okay? So this is going to be, this part right here is interpreted as the expected value of the function h of x, okay, where x is a random variable that has PDF equal to f of x, okay? This f right here, this defines the PDF, okay? I don't know, draw that. The PDF of x, okay? So when we see expected value over f of h of x, that's what it means, okay? It's the expected value of this function h of x, whether that h of x is p, you know, when we're just talking about the mean, if we want the expected value of p or x or whatever, or it's p squared or some other function, it's the expected value of this, okay? And this side is going to be, is equal to the integral over the domain of x, okay? That's what this curly x is, integral over the domain of x, okay? So for beta, it's going to be 0, 1. For normal distributions, negative infinity to infinity. For exponentials, 0 to positive infinity, okay? So whatever the domain of x is, and it's going to be of, basically, the function of interest h of x times PDF of x, okay, dx. Okay. So let's go back to our problem, okay? We have, after observing the data, we say P comes from the beta distribution with this, which means that the PDF is 1 over beta 85, 225, p to the 85 minus 1, 1 minus p to the 225 minus 1, okay? So we have this. After observing the data, we know that p is this, and we want to know basically 3 choose 2, p to the 2, 1 minus p to the 1, which simplifies to 3p squared, 3 times p squared minus p cubed. All right, so now I have my two parts, okay? So here, what we want is we want to know what is the expected value of this question, okay? What's the probability of getting 2 hits out of 3 at-bats, okay? We want to know what's that expected value if we consider every single possible value of p, okay? Because right now we don't have a single value for p. With frequentist, we did. With frequentist statistics, we did have a single value for p, and that made our lives easier. But when we switch to Bayesian statistics, we do not have a single value estimate for p. We only have a distribution. We have a distribution, and that's what makes Bayesian statistics, more useful and more flexible, but also more complicated, is that we don't have a single value, we have a distribution. So what we want is the expected value of this thing, even though we don't know exactly what p is, okay? So we're going to let this be h of p, okay? So let this be h of p. And so what we have now is the expected value over f of h of p is going to be equal to the integral, considering all possible values of p from 0 to 1, of 3 times p squared minus p cubed times the beta distribution, which is going to be 1 over b85, 225, times p to the 85 minus 1, times 1 minus p to the 225 minus 1 dp. Okay. Is that all right? Getting to this spot. Okay, so this part is the h of p. All right, well, whatever. Okay. Okay, so this is what we want to do. This is the question we want to answer now. And I don't know how do I copy this? All right, there we go. Okay. All right. So if I see this, and you ask me to calculate this integral, I don't know what to do, right? I go to Wolfram Alpha, I type this in, and I hope it can spit out an answer, right? Because, I don't know, it's been a while since I took, 31B, where you do this? I don't know, okay, where you do the integration. Integration is hard, right? You get like the table of integrals, and it's not easy, and you can do like integral by parts, and there's all these different rules. I forget, right? I don't know how to integrate this. Does anyone know how to integrate this? Maybe, like, yeah, you'd have to expand it, and then, I don't know, what are you supposed to do with 1 minus p to the 225, right? So this is hard, okay? This is hard. And this is where we start using Monte Carlo methods, okay? Where we just say, well, this looks hard. Can we get an approximation with the computer, okay? I mean, there's a few ways we could do it, right? We could do like a Riemann sum, and we can take like every value from 0 to 1 and go increments by 1,000 or something small and calculate and multiply and stuff like that. Those are all possible, but this is a perfect situation where Monte Carlo integration can help us get an approximation to this answer, okay? So Monte Carlo integration will give us a good approximate answer. Okay, so Monte Carlo integration will give us an estimate of this quantity, and we do not have to do a difficult integral. I don't know, anybody willing to type this into Wolfram Alpha and see if it spits out a thing? I didn't bother, but you can. Okay. All right, so this is what Monte Carlo integration says. And it's like almost anticlimactic. It just gives you the answer right here. It says, okay, well, if you want this, then this is the answer, okay? All right, so this represents our Monte Carlo integration estimate. Okay, and what this says is just basically the mean, and it's actually right here. It just says computed by doing mean of h of x. And then it gives you some more stuff. Since h bar sub n converges almost surely for all every blah 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 by strong law of large numbers. I don't know if I want to like. I don't want to get into the strong law of large numbers. You guys did something related to that or no? No. You guys know the law of large numbers, right? Which states what? Something like if you take a big number of things, it should approach the theoretic thing, sort of. It's a lot more formal, yeah.
Isn't it that if you input more numbers into like I want to say sample or population, it will converge into the central limit theorem, the bell-shaped curve? Or is that not it?
That's not necessarily that it'll converge to the central limit theorem. They're related, but the law of large numbers basically says that the samples should approach basically your theoretic thing. But it's more complex. I don't know, did you learn about modes of convergence? There's like convergence in distribution and convergence in, I don't remember, other stuff. There's like 4 modes. I forget, I apologize. Okay, but anyway, this is all we do, right? It just says mean of h of x. This is the, it's not, that's the answer, right? So this is 1 over n of, this is basically equal to mean of h of x, okay? And the key is that x is drawn from the beta distribution with shape of parameters 85 and 225, okay? And with R, this is really, really, really easy, okay? So just draw n samples, okay? N samples like on the order of thousands or 10,000s, maybe even millions, okay? And with R, this is super easy, right? What do we type in? If we want random numbers from the beta distribution, all we do is we say R beta, give me like 100,000 of these things, 85, 225. And then that's it. And then we take these things, so we'll split this into like, we can call this X or XJ. I don't know. Does the textbook use something? It does not.
So it's going to be a vector, so it's not a.
Yeah. Okay. So we'll just call it the vector X, and then we just ask for the mean of basically h of x, all right? And then so you'll just need to set up a function for h of x. Shall we do this? Sure. Now I'm curious. Okay, did anyone go to Wolfram Alpha?
Yeah, it worked, but I didn't put in the constant.
You didn't put in the constant. Okay, so we'll try it. All right, so we'll say integral from 0 to 1 of, okay, so I'm going to do 3 times p squared minus p cubed times 1 divided by b 85 225 times p to the 84 times 1 minus p to the 224 dp. Okay, all right, Wolfram Alpha, go. Oh, look at you, showing off. Okay, what is this? That's not helpful. I want a decimal answer. Plus a constant. Can you imagine? That'd be so sad. Okay, what is this? Okay, this is my answer.
I think that the beta part.
That's a big thing, huh? This is really, okay, so I have to multiply this by this constant here? Okay, all right. Well, what is this constant, Wolfram Alpha? Parity even. Oh, I should have typed in beta. Okay, all right. Let's just try this. Oh, I'm so scared now. Okay, maybe it'll give me a real number though. Okay, so this is a really small number, 10 to the negative 80. I know. Okay. Input result. No, it didn't like it. Didn't like it. Okay. All right. So I've got this decimal approximation times this thing over here. All right. I'm gonna put that in there. All right. Let's ask what this is approximately equal. Okay, 0.164. All right, that's something I can live with. All right, that sounds reasonable. 0.164, approximately. So it's a lot. That's a lot longer than that. Okay. Well, let's go to R and try this out. Okay. So what did I say we're going to do? We're going to do X is R beta. Let's ask for like 100,000 of these things, okay? And then we're gonna say H is a function of X, and it's gonna return what? 3 times P squared minus P cubed, right? Okay, and then, and we want mean of H of X. All right, this is a lot easier, right? Even with the help of Wolfram Alpha, all right, let's see. We're hoping for something close to 0.164, because that's what Wolfram Alpha said. I'm nervous now. Oh, wait. Oh, of course. Rookie mistake here. All right. Look at that. 0.1640936, okay? Are we not impressed? Are you not entertained? Okay. So this, So this is Monte Carlo integration, okay? We're okay with the fact that we're not gonna get an exact answer, okay? If you want an exact answer, Monte Carlo integration is not gonna be the way. You gotta do it analytically, okay? But we can see that trying to do something like this analytically, maybe there's a shortcut, okay? But we can see that it's going to, it's a bit of a nightmare, right? So, I will just do this. Okay, so we got this here. There's your answer. Where that's that. Okay, and then compare that to. I should have saved all of this stuff. Here, we'll go back to this thing. I don't even know what this says, but something crazy, right? All right, so this, you know. And we saw this is almost a cartoon, right? Like this long. Okay, well, just for fun, we'll throw that in there too. We don't even need the whole thing, that's fine. Okay, so so this is the Monte Carlo integration. Where basically, just, you know, from the classical perspective, all we have to do to calculate some value here, right, is, you know, this is the thing that we want. And in our case, it was what's the probability that the player will get 2 hits in the next 3 at-bats, okay? But again, we don't have an exact value, and we just plug in, we have to plug in all possibilities for what that batting average is, okay? It could be 0.2, it could be 0.3, it could be 0.4. Each of those have different probabilities. And so we approximate it using this, okay? We can estimate the variance as well, okay? Just by kind of plugging in, we take, I guess I'll continue on here, okay? So, you know, estimate the variance in the same way. Okay. So, so this is the variance. This is the true answer to get the variance. Okay, so this is how we get that. But then in R, we can just calculate the variance this way. Okay, so the estimate of your variance so you just do take each value h of x minus h bar, and then you square it, and then you divide by 1 over n squared. Okay. And again, you know, this would be much harder to do from the analytic perspective. Okay. And then you can also kind of approximate using the central limit theorem. you can create kind of confidence bounds to because this is going to follow the normal distribution here. Okay. And so for kind of these classical, for any kind of standard distribution, okay, R will have a generator function. So for all of those, you know, on the Wikipedia, when you go to this list, conjugate priors, okay? Okay, so it's got kind of the list of all of these things. You know, most of these distributions exist in R, okay? If you want random values from the beta distribution, you type in R beta. You want random values from the gamma distribution, you type in R gamma. The Dirichlet distribution, I think you have to install MCMC pack. There's a library for it, but it will do it as well, okay? So you might have to, some of these you might have to load an outside library, but you know, normal, we're very familiar with that, R norm, and then there's all of these other ones, right, that are lesser used, but like the Wishart and stuff, which don't ask me about right now, but you have, you know, so you have R beta, R gamma, R norm, et cetera, et cetera, et cetera. Okay, so I guess, shall we just try another simple example? It's like the exact same one. All right, so, okay. So we've been going off and we've been saying, you know, batting averages have, we're going to assume that the prior distribution is going to be beta 81, 219, okay? So let's say we've observed, we still have a, you know, a new player and we've watched him play in, you know, half the season or something. Okay, so now we've observed many more at-bats. Okay, and the new player is doing very well. And we're going to say we've had, let's say, 300 at-bats, and we'll say 100 hits. Okay, so in what we've observed, he's batting, you know, 333, which is very good. Okay. All right. So let's just say we ask. Okay, so find the posterior distribution. And then we'll ask, what is the probability that the next at-bat is a hit? Okay, and you know, for this question, so find the posterior distribution, you should be able to do by hand. And then what's the probability that the next at-bat is a hit? Just, you know, write 3 lines of code. Maybe even just 2. To answer, okay? All right, I'll let you guys work on this for a couple of minutes. We're gonna, I guess class ends in a few minutes anyway, but just, I think we can do this. All right, so try it out. You can talk to your neighbor if you need to, or explain to your neighbor if they're not sure.
One line of code.
Yeah, you could do it in one line of code.
No, I'm joking.
How are you guys doing? I think it should be higher than that.
Isn't it just a mean of
All right, let's try this out. Okay. So a new player, we've observed many more at-bats, 300 at-bats, 100 hits, okay? So what is the posterior distribution? The posterior distribution will be beta 81 plus 100 and beta 219 plus, well, 100 hits equals also 200 outs, right? We have a total of 300 at-bats, so we have 219 plus 200, okay? And so this becomes beta 181 and 419. Do we feel okay about that? And if we weren't sure, you could do the likelihood, which is going to be p to the 100 times 1 minus p to the 200. This is the likelihood, and then the prior is proportional to p to the 81 minus 1 and p to the 1 minus p to the 219 minus 1, and then when you combine them, you're going to get this. Okay, and then so the code is basically x is going to be r beta. Maybe we want like 100,000 of these, 10 to the 5 or something, okay, or 10 to the 6. It's really like r will generate 1 million of r beta values very quickly, okay? And we say 181, 419, and then what's our h of x, or h of p? Our h of p is just p, right? What's the probability that the next at bat is a hit? It's just h of p, is p. So now we just say mean of basically h of p, which is just going to be x. All right, and I think this is going to be close. So if I say x is r beta, we'll ask for 1 million of these, okay? 181, 419, okay? And then we're just going to ask for the mean of that. Okay, and we get 0.30167. What would the what's the answer if we did classical MLE? Okay, so classical MLE would say, okay, you've got 100 hits, 300 at-bats, p hat is equal to 0.3333, and that would just be your answer. Okay, so what's the probability that the next at bat is a hit? It's going to be 0.3333, whatever. Okay. All right, so this is just kind of our first taste of Monte Carlo integration, and it's very easy when paired with R's ability to generate random variables from known distributions. Okay. All right, we'll end there. We'll see you guys on Wednesday.